I will talk about the use of EGR and the influence of its temperature on spark ignition ethanol engines. The authors are Antônio Pacífico, Cleiton Zabel, and me, Luana Camargos. Exhaust gas recirculation consists of extracting part of the exhaust gases and insert them back into the engine intake system. In this work, the focus of using EGR in spark ignition engine is to reduce nitrogen oxide formation and increase the efficiency of the engine at partial loads. NOx formation is reduced because the insertion of EGR, an inert gas, decreases the peak temperature of the combustion chamber, decreasing NOx formation due to the Zeltovich mechanism. The increase in efficiency occurs because with the addition of EGR, the throttle must be adjusted in a less restrictive condition, imposing a higher pressure level in the intake manifold to provide approximately the same mass of pressure mixture, how we can see on the picture here. This less restrictive throttling condition results in less pumping work, but there is a trade-off between the maximum EGR rate to be used and the benefits that will be achieved, as increasing the rate of diluent in the cylinder can also cause instability in combustion. In addition, the effect of EGR temperature on efficiency was verified. So the engine used for the test was 1.2 liters of displacement, 3 cylinders, naturally aspirated, port fuel injection with double variable valve control. A mixer already designed in a previous work was used and an additional swirler was installed after the accelerator in order to equalize the mixture in the 3 cylinders. Spark plugs instrumented with piezoelectric sensors were used to measure the indicated data. Emissions were measured by Oriba Maxa 200, and this work focused on one of the 5 representative points of accumulated fuel consumption in the Brazilian emissions and efficiency test defined in a previous work. The point is 2,750 rotation per minute and 25 Newton meters. The tests were divided into 2 parts. In the first, the temperature of EGR was fixed at 25 degrees Celsius, and the concentration was changed for the Miller and Otto cycle. In the second part, only for the Otto cycle, at the point of minimum brake-specific fuel consumption, the EGR temperature was varied from 20 to 55 degrees Celsius. So how we can see on the results, it was obtained a significant reduction in the concentration of nitrogen oxides emitted, as expected in both cycles, Otto and Miller. But it was not seen any gain in efficiency with the use of EGR in the Miller cycle. This occurs because the Miller cycle already retains residual gas inside the cylinders, the so-called internal EGR. Hence, despite of the reduction in pumping, there is a worsening in the combustion that does not reduce fuel consumption. For rates above 10% of EGR, combustion is unstable and the brake-specific consumption worsens. The unburned hydrocarbon starts to increase with 6% of EGR rate, indicate combustion deterioration. However, for the Otto cycle, it was possible to obtain a decrease of 2% in brake-specific fuel consumption at a rate about 16%, and the only stability in combustion was observed is in this point of 24% of EGR, where total hydrocarbon increases significantly and the brake-specific fuel consumption worsened. For the next steps, we focus only on this point. So, with the fixed EGR rate at 16%, the temperature of EGR was variated from 20 to 55 degrees Celsius. And to keep the break mean effective pressure at 2.62 bar, there was an increase in the intake manifold pressure, indicating a reduction in pump work. This gradual reduction we can see in the low pressure of the indicated diagram. Talking a little bit about the combustion, for the temperature levels tested, combustion seemed to happen a little earlier and a little faster when the mixture temperature was increased. The combustion phase and duration calculated by the recirculation analysis show it, and it's here. The trend lines indicate that crank angle location corresponds to 5 and 10% and 50 and 9% Burnett mass fractions are happening early in the cycle, and there is a reduction of 0.02 crank angle in combustion duration for each degree Celsius in mixture temperature increase. About the combustion stability, the coefficient of variation of the indicated mean effective pressure show almost the same condition for all temperatures, so the temperature not affect the stability of combustion. As a consequence of keeping the same Bmap and Emap, if one considers engine friction remained constant for all tested cases, the Emap high suffered the same absolute reduction of Emap low. The maximum observed reduction of 50 millibar in the pump work at 55 degrees Celsius compared to the 20 degree Celsius case was accompanied by the almost same reduction of 49.8 millibar in gross mean indicated pressure Emap high. This reduction corresponded to minus 1.2% in Emap high, which would lead to a reduction of the same order in fuel consumption. However, the specific fuel consumption of the engine varied according to this plot. This plot normalized to the point at 20 degrees Celsius, indicating a maximum reduction of 0.26% at 40 degrees Celsius instead. In spite of having a decreasing trend with the increase of mixture temperature as expected, the measured fuel specific consumption value was higher than expected and could be explained by the measurement uncertainty of the fuel consumption meter, which is around 1%. The results show that, spite of the gains in the pumping work and observed trends of faster combustion with higher mixture temperatures, the overall cycle did not promote differences in efficiency that could be captured by fuel consumption measurement device. The work is still in progress, and it is desired to reach higher temperatures, about 90 degrees Celsius, with the installation of heater in the EGR line, which will allow analysis at higher mixture temperatures. Improved ways of measuring fuel consumption are planned as well. So our conclusions for this work is EGR is efficient for reducing NOx emissions when applied to spark ignition engines. Ethanol is more tolerant to dilution in relation to what is reported in the literature for gasoline. The efficiency gains of 2% obtained with EGR when engine operates in Otto cycle are significant given the large number of engines in the market that do not count on dual VVT and operate in this mode. For the temperature variation range obtained with the current EGR system, the observed brake-specific fuel consumption values have fallen inside the fuel measurement device uncertain range, not allowing a concrete conclusion. Additional studies need to be conducted, coupled with simulations and experiments. I would like to say thanks to São Paulo Research Foundation, Instituto Mauá de Tecnologia, University of São Paulo for all support given to this work. And thanks for your attention, and bye-bye.